We also need to look at the year-to-year variability or decade-to-decade variability of the climate. We've been saying global warming, climate change, paleoclimate, but what is the baseline on which these things are acting, right? So we mentioned El Nino, we mentioned monsoon. These are natural variability, also referred to as internal variability, because they are produced by the feedbacks within the atmosphere, ocean, land, vegetation, glaciers, and so on. So looking at the mean temperature distribution of the ocean temperatures, you can see the nice warm pool here, the warm waters under the ITCZ, and the Gulf Stream and the Kuroshio here, and the Indian Ocean's special status, which is not so obvious here. So ocean is several kilometers deep, has very high heat capacity, so obviously it can store energy and provide the memory for low frequencies of climate variability that are not directly driven by day-to-day variability of solar radiation, sunset, sundown, versus seasonal variability of radiation. So internally they are generating these low frequency timescales. So natural variability and forced variability have to be separated. Again, forcing is perturbation to radiation, and radiation is resulting from the greenhouse gases like carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, which are the prohibited refrigerants, but now HFCs are also contributing a lot. So this is looking at the effective radiative forcing imbalance, short wave minus long wave, how much is being added by these particular constituents in the atmosphere. So this is also talking about confidence here. We have high confidence about this. Stratospheric and tropospheric ozone. Stratospheric ozone is great because it absorbs UV and energy, so it actually provides a small negative forcing, cools the atmosphere, whereas tropospheric ozone, which is produced from precursors like methane and carbon monoxide, water vapor, and so on, is bad for health, but also a greenhouse gas, so that has a contribution with which we have medium confidence. Sulfate coming from industrial activities and coal burning and so on are scattering, so they actually cool. So when you clean up the atmosphere, in fact, you may increase the global warming for a short period, but you will have huge co-benefits on health. Okay, but eventually you want to get rid of these pollutants anyways. So these are broadly classified as aerosols because they are airborne particles of various sizes. Black carbon absorbs, has very low confidence on what it's doing. Organic carbons from fossil fuels produce a little bit of cooling, but very low confidence. Biomass burning. Indirect effect of aerosol is where aerosols modify cloud properties, cloud brightness, droplet sizes of the rainfall, and so on, and that's called indirect effect. So large uncertainties right now in that. Land use, just the albedo change, reflectivity change because of deforestation, urbanization, etc. can provide some cooling. Forests are darker, deserts are brighter. Okay, but do we want deserts instead of forests? No. And solar forcing is a tiny bit, and it doesn't explain the global warming at all. So you will see some people arguing that that contributes. Okay, so this is again looking at the same thing, radiative forcing, but now it is looking at the human activities that produce them. So the same things being shown in a different orientation. So long-lived greenhouse gases, ozone, stratospheric water vapor. So global warming is increasing water vapor in the stratosphere, which is not a good thing. We won't get into the dynamics right here. Surface albedo changes because of black carbon on snow. What happens if you put black carbon on snow? Carbon absorbs radiation, so the darker snow melts faster. In fact, there is some argument that the little ice age that ran during the 15th, 16th, 17th centuries ended because of industrial activities and increased aerosols and black carbon on glaciers. Okay, total direct effect and cloud albedo effect of the aerosols and contrails from ships and planes, so solar irradiance. So there is a total net radiative forcing from human activities. As I mentioned before, we have to worry about greenhouse warming potential of a particular greenhouse gas, its residence time, and its amount or concentration. This is just running quickly through the greenhouse gas potential and lifetimes. So carbon is somewhere 50 to 100 years, methane 12 years, nitrous oxide 120 years. HFCs depends on which variety it is. Perfluorocarbons up to 50,000 years. It's crazy. Sulfur hexafluoride, which is a product of cooling and refrigeration, is 3,200 years. So this is the relative impact on global warming the other gases would have over something like 100 years. As I mentioned, it's not a very solid measure because CO2 exists for a longer time and so on, but it's a good indication that methane is much more powerful as a greenhouse gas than CO2. We consider CO2 as a reference. Nitrous oxide is terrible. HFCs are much worse depending on which one it is. So if you have greenhouse warming potential of 11,700 years lasting for 209 years, that's not good at all, right? Perfluorocarbons, sulfur hexafluoride is 23,900 times, and these are the various sources that are being shown. Okay, so maybe I'll do the patterns in the next podcast. Just looking at the radiative forcing is an important thing. Make sure you understood the concept. How long the gases last is going to matter. How much more powerful they are as greenhouse warming gases compared to CO2 is very important, and what their concentration is and how fast we are increasing them is also important. So Montreal Protocol tried to eliminate CFCs, which is mostly working, and they added HFCs to it under the Kigali Amendment. Replacing HFCs is now a urgent call under Paris Agreement as well, but there are details there as well.